start, hello, service, right? So what's going to happen now is Fleet's going to push that service into etcd, and it's going to make a decision on who's best fit to run this container. And one of the criteria was it had to match certain metadata, so we can guarantee that this thing won't land on an etcd machine. It's going to land on one of these Kubernetes machines. And it already picked a machine. So now I can do fleet, list, units, and we see that they're in different states. So right now, it's in the pre-start state. It's probably pulling down the Docker image, getting ready to run the command. So all of this is asynchronous. We found the host for the machine. It's actually running. And I'm doing all of this from my laptop. I'm just interacting with the scheduler remotely. I can also do fleet, journal, and then we can watch this service do its thing. Let me delete my known host because the key has changed. So Fleet does this thing over SSH. So what's happening now is this is the log from the server that ended up winning the election to grab that workload. And using Fleet, Fleet knows where that machine is. All I need to do is say, I want to watch the logs for a service. So now we're interacting with the scheduler. No one needs to know the host name. So what we're starting to see is a bunch of tools built on top of this. So the contract we have here is, I need one of these running in the cluster. Fleet, you decide. We'll talk about more complex scheduling, later if you have questions. And Fleet found this, and Docker's doing its thing, right? So if everything's working at this point, we can ask Fleet again, what's the status of this particular container, and it's actually running. So if that is true, I should be able to take this IP, go to my web browser, and it works, right? So no one's logging into servers, no one has to have special system administration skills. You just need to be able to understand what the contract is. You build a container. In the case of Fleet, it's a systemd unit file. In the case of Mesos, they have a different description file. In the case of Kubernetes, it may be a JSON file. But at the end of the day, the workflow still looks like this, where you're giving the cluster a unit of work, and it decides where that goes. And that's a big change for a lot of people because everything has been the magical host names, right? This host name is important. So what's the other benefit of having the scheduler in place? So what we did before schedulers, remember we said the ops team was the scheduler. When the machine went down, there's the thing we do, right? Where we sleep with one eye open, you get a phone call saying machine is down, everyone goes crazy, and you get to listen to the rest of your team members breathe on the phone until about 1 a.m. And because you're trying to restore the service, right? You want to reboot the machine. And I laugh every time because it's really silly. Everyone knows what needs to happen. So what you do is you encapsulate what needs to happen into the scheduler. Scheduler, if this machine goes down, just start it somewhere else and let me sleep, right? So let's just try to see what happens when we do that. So Fleet control list machines, and it's on this machine 42. And let's just log in and simulate the failure. Well, failure usually doesn't result in someone logging in, right? If you log in, you might as well just quit your job. Let's say you accidentally delete the machine that's running. So wherever the guy's running 42, VMware doesn't make it easy. I'll just log in. So you go in 42, someone's doing what they shouldn't be doing. They type this command, and now it's off. So at this point, the service is down. It's gone. So what we want Fleet to do, we want Fleet to honor the contract, right? We want Fleet to guarantee that that service is running somewhere in a cluster. We don't care where, just an eligible machine. And so there was another machine, and the only criteria was that it had to have metadata equals Kubernetes. It found a new machine and started the service on that machine instead. So now that machine is going through its paces and downloading the container, and eventually it will start, and it keeps it running. So it enforces the contract. Ideally, you want to have more than one node, so that way you're not just down for a period of time. But you can imagine a case where you're having 3 or 4 of these, and you over provision so that way you have enough capacity for things to move around the cluster, right? And this is how Google does this thing. So when they have workloads that need to, let's say, index the entire internet, you have a bunch of machines that may have capacity, but no one has time to keep the accounting. You just want the scheduler to figure out who has capacity. If so, let them run this container. And then when they're done, remove that container, and now we gain back the capacity. So now you start thinking about the entire data center as one big operating system. And now you have one global init system that's starting and stopping services, reading the journals and the logs from these machines, and now it's running again. So if this is actually working, one second, I'll get to your question. So if this is actually working, I should be able to grab this IP and hit port 5000, and we're back up and running, right? And this is what the scheduler does, right? This is a very simple use case of that, but this is the whole goal of being able to interact with the cluster. You have a question?
Yeah. So this is a situation where there's no high availability, which means that it went down and the other is coming up, which means that I have an outage. It's not that I've synced the states and this guy takes over.
Mm-hmm.
This guy like that.
Yeah, so normally what you're going to do in production in real life, you're going to have 10, 20 hosts. You're going to do something like run 3 of these, run 5 of these. And most load balancers are smart enough that when I go to proxy to that backend and that machine is gone, then I need to try to request another machine in the list of backends, right? And there's no such thing as zero downtime. It's a fallacy, right? You can never have zero downtime. Right. Everyone goes down. What you don't want is long outages where 15 minutes goes by and no one got the page. So you want a self-healing architecture where maybe you did drop a few connections. Okay, you can live with that. What you can't live with is the outage report where it was down for 20 minutes because the failover mechanism failed, right?
I just want to understand sort of where CoreOS ends and Docker begins and where that differs from just sort of a generic Ubuntu image. If I just had etcd running and the scheduler, as it's indicated there, could I do the same things that you showed in this demo?
You can absolutely do the exact same thing with anything, right?
Okay.
If you wanted to build an Iron Man suit, you can go buy all the parts and become Iron Man. Well, we see most people fail, like, because it's been like 15 years and people have been failing horribly at trying to build a minimal system because no one can agree what minimal means. So we just did the Apple approach. We're going to make a decision for you. There is no way you can log onto the server and do yum install anything because it's not there. You can't even put it there. So some people get mad at us, like, hey, I want to install actually. You can't, sorry, we're never going to do it ever, ever, ever. So now we force the model of you have to use a container. So naturally when you see someone using CoreOS, you can bet for sure they're using containers. So it's the idea that we reinforce. And then we do everything to make sure that it's easy. So when Docker first came out, it was really hard to figure out what features you were going to get. If you're on an old version of Ubuntu and it didn't have all the namespaces in the kernel, certain features didn't work. So we make sure that all the features of Docker work out of the box. We figure that's our job at the OS. And we like to say if we're successful, then the OS shouldn't matter. Ideally, everyone moves to this model where you stop trying to pick up an OS because of packages you need on the OS. You just want someone that can run the container and you move on. We're more interested in distributed computing. This is why we built etcd. This is why we built Fleet. I'm a core contributor to the Kubernetes project. These are higher level things that we think are really, really important. We built the OS because we had to. We needed something really slim and had all the latest and greatest features to make this stuff work today. So that's why we've done that.
Could you explain how the Kubernetes and CoreOS relate to where does Kubernetes stop and where?
Yeah, it's a good question. So we stop, CoreOS itself stops at the OS. Here's an OS, it's running Docker. That's where CoreOS ends, right? We have a read-only file system that we automatically keep up to date for you so that we always run the latest and greatest Docker, etcd, and the components that you need. That's what we stop, right? We're the UPS truck. That's it. Now, Docker handles the containers. We let Docker do its job. We have our CTO is one of the top 5 committers in Docker project. So Docker handles containers, and we let it do that thing. Now, when it comes to orchestration, one thing we need is a tool like Fleet to set up something like Mesos or Kubernetes. So I have another demo where I take Fleet and I install all the Kubernetes components, right? We don't have time to do it here, but Kubernetes has like 5 or 6 daemons that you need. Some of them need to run on all the machines. Some of them only need to run on 1 or 2 machines. With Fleet has an idea of a global unit file. So I can say that this particular process needs to run on every machine in the cluster. And remember, we don't know what every machine is because that state can come and go. So Fleet's idea is to make sure that the Kubernetes services are running everywhere. So there's a little tool called the kubelet. And the kubelet is the thing that gets things that it needs to run, but it needs to be everywhere for this to work. So Fleet's job is to say, any machine that comes up in the cluster, you need to be running kubelet, right? You have this bootstrapping problem. So on purpose, by design, we kept Fleet very minimal. But I have some tools that I've written against the Fleet API, so I know how many machines are. So if I want to auto-scale a Kubernetes cluster, I can just bring in new machines, Fleet Global Unit will kick in, put the right components in there without me doing any extra work. Once that machine is up, I can talk to Fleet and say, give me all the machines that are running the kubelet service that have this metadata and register them with the Kubernetes API. So you need this lower level orchestration layer to keep that other system running. And then that becomes your primary interface for deploying Docker containers. But all the way down the stack, these are just different abstractions on who launches this Docker container.
Not just a question, but how many, without using the VM, how many CoreOS per hardware box and how many Docker instances per CoreOS?
So it's just like your same limitations on the Unix process, right? So the overhead is very minimal. Like we said, it's just containment and using kernel features. So if you have enough memory to do it. So one thing we didn't talk about, Kubernetes does try to leverage a thing called cAdvisor. So cAdvisor helps you track how much memory and CPU you're using, not just right now, but over time. And imagine using that historical data to decide who should get the next workload, or maybe even dynamically move things around the cluster at different parts of the day. So the number of the density you're going to get is going to be much higher, right? Because we're not, every service now doesn't consume, like I think nowadays most OSs need 512 to a gig of RAM to boot in a VM. And most people are just wasting that memory to just run one service. That's a very common model, 1 VM per service. And with containers, you go 1 service per container. And now you're down, if we look on this box, let's look at the overhead really quick. We're on this machine here, and if we were to actually look at it, remember it's just a normal process. So we log into this box, and I just do a top, and we're looking for the hello service here, and it's here, and we're using 6 megs of RAM for an isolated process using containers. So the overhead is way lower, right? If I wanted to spin up 25 of these, it's going to be 25 times 6 versus 25 virtual machines.
Sorry, I didn't ask about overhead. If there's any inherent limitation on the how many Docker instances can you run on the single core OS?
No, you can run as many as you have memory for.
So one core OS can run any number of Docker in.
Yeah, the limitation to me would be your
How many core OSs per machine is the single core OS from hardware?
So if you have a single CoreOS host, you're talking about how big can a cluster be?
Physical hardware, physical machine. Then you are running single core OS only.
Yeah, so so I don't understand the question. So it's like you're talking about from a performance perspective, how big is the box normally?
Usually, if I run a Linux and hardware, I run multiple Docker images. Since I'm trying to figure out if CoreOS is similar to Linux.
Yeah, CoreOS is just a Linux.
And why? Yeah, and I don't see a very difference between Linux kernel and CoreOS, except the tools you are coming in.
Yeah, so CoreOS is a Linux distribution, right? So like Red Hat, Ubuntu, they all have opinions about what it takes to have an operating system and tooling. So in the Red Hat world, you get RPM and SE Linux and things like that. In the CoreOS world, we give you Docker out of the box. So remember last year, when no one was sure Docker was going to actually work out, we shipped CoreOS, Docker enabled by default. And that's the model. That became our way of delivering packages. It's gotten popular now, and everyone seems to agree. So you have to have this to move things forward. We can't wait for everyone else to agree that it's a good idea. Sometimes we got to push it forward.
It seems we are restarting the application. So is there any work going on basically for container migration?
So you're talking about like migrating the containers?
Right.
So the container world is totally different from the VM world. So the VM world, yes, you have the features of live migration, where the storage follows the machine. It's really just the cluster file system underneath the hypervisor. So people are doing some of that idea with CoreOS. Like there's a big push to get Ceph. There's some vendors that are shipping, like I think even Deus is doing this now. They just launched a new version of their PaaS product that has Ceph built in, so now you have distributed storage across all the machines. But containers really work well with the 12-factor model, where you have a lot of stateless processes. For most organizations, 90% of your apps are stateless, but then you do have a database. If you have a database, do not try to move it around the cluster dynamically. There's no reason for that. Usually you need data locality. So what most people are trying to do with their containers is you take your container, itself should be stateless if you can, and push your data into a database, push your files into a block store if you can. So idea is to keep these containers very small, where they don't need to say, oh, it can only go on this machine with this particular data volume. That kind of locks you in and loses a lot of flexibility. So migration is not a thing, it's more like launch another one.
Yeah, you mentioned about Italy, you mentioned basically that, I don't want to start the Hello service on the same machine where the HCD is running. So how do you
How do I enforce that?
how do you configure that?
So what happens is, so Fleet itself has a bunch of metadata options. And if we look at this hello service, so systemd allows arbitrary metadata. So down here in this Fleet section, we're being very specific. We're saying that the machine metadata needs to have this key value pair. I can also specify certain services to follow other services. Like in the case of Kubernetes, some services need to live by each other. So what I could do is say, this other service, it must be deployed where this other service is running, and let Fleet sort it out. So if Fleet moves up a service, the other one will follow, right? And the scheduler will do that with metadata.
So in case, let's say I want to make sure that I run only one hello service in each of the physical machine.
You can have a conflicts metadata. So there's a conflict section in Fleet. I'll show you the complete list. So the conflict section allows you to basically, so we have one here, a good example. Here we go. Let's see if I can make this a little bit bigger for you. So you notice here, we're going to run multiple instances of Apache. And what we're saying here is that it conflicts with any other thing named Apache. So wherever we name the service, we can say they conflict together, and they should never be co-scheduled. And what that means is if we need 3 and there's only 2 boxes, one will just sit in waiting state until a new machine arrives.
So you mentioned about overlay file system, right?
Yep.
So does CoreOS allow us to make a decision on what type of overlay file system we use?
You talking about cluster file system or overlay network?
The file system, just the
Yeah, so right now we ship ButterFS by default, and mainly for the copy on write semantics for the containers. But you can load up another file system if you want. Like some people are even running like ceph and clusterFS inside of containers, because you can, and then having distributed data that way. By default, all of our stuff is ButterFS.
one more question. Is there a way to limit the memory usage of a container?
Yes. So Docker allows you to, if you look at the command line flags for Docker, they get really long. You can be like, no more than this memory CPU, all the C group stuff is exposed. Some of these other schedulers like Kubernetes also have metadata that will say memory allocations and things like that. Far back and they'll get you.
Yeah, so how CoreOS partition memory between different containers? For example, one app need more memory during by executing the application. So how it allocate more memory to the container?
So remember, containers are just processes. So if you don't give it any limitations, they're unbounded, just like your standard processes today. They will eat up the whole box and kill you. Or with Docker, so since you're being launched in the container, you can give the C group specification up front. So I'll see if I can find you an example. Docker run. Oh, is that like go home? All right. Is that a hint? Is it down here?
No, I think we're fine.
Okay. Let me find it.
So that means the same page can share between different containers, right?
Yeah, so here you go. So here's one option, -M to limit the memory, and -C to limit the CPUs. And it's really weird when you look at the CPUs the way it's weighted. It's like you say one gets 100 and one gets 1,000, then it becomes relative. So you almost have to use the same units across. But this whole C groups thing really got pioneered by Google. This is how they make sure that they can get maximum density on a machine. And once you start giving each unit that you launch these memory limitations at runtime, then you can almost guarantee that you're going to have certain capacity levels on each machine. And something like CAdvisor allow you to report the utilization and actually do intelligent decisions based on that. I'll get you to come back.
What do you do everything in Go?
Why do we like Go? Oh, it's cool. It's new. Well, the reason why we like it from a performance perspective, and it's really easy to teach new developers that come in. So we have a few people on the team that come from a C background. Our CTO is a kernel developer when he was at SUSE. And we just like the format. I mean, for all the stuff we build, a lot of these networking services, it's really a good fit, has really good C interrupt. So when we're interacting with the kernel, we have to go down to the C level. C goes really nice. And the deployment footprint is really nice. So since we don't deal with a package manager, we don't want to ship a bunch of libraries all over the place. Having this ability to do these static binaries, if you've never used it before, it compiles quickly, and it just kind of fits the use case for the services we built.
So you mentioned I can specify the -m option, right? So I've seen many enterprise applications where they rely on /proc meminfo, and they read that memory and try to allocate that much memory and always fail. So how do you handle cases?
So your container is free to do that. Well, first, you're going to be contained, you're going to get a different view of the world, number one. And then you can try to allocate, but the kernel's going to stop you because you've been contained. So you're going to try to ask for that much memory, it's going to be like, no, I will not give you that much memory, even if it's available. That's the whole power behind the whole secrets implementation.
Regarding the CoreOS, you said that you did upgrade. You have to bring down the entire system, or do you cannot?
Yeah, so usually to apply a lot of the kernel updates, you have to reboot the system. I mean, there's tools like kexec, but it's not 100% stable. So right now, we recommend people reboot the system. But when you think about the architecture is, you over-provision, and your app should be able to survive reboots. A lot of people don't have apps that can be rebooted, right? It's like an event. You reboot the app, everyone gets paranoid. But we can't exist in that world where everyone has to be careful. That won't work well in a system like this. You need apps to be able to be destroyed.
So does it coordinate with the fleet? So that fleet doesn't really schedule someone container on the same mission so that you never...
Yeah, so that's what all the metadata does. So you sort that out in your specification. You said these things conflict together. I need 5 of them running. And then you start rebooting machines, the fleet will sort it out for you. You can pin things to a specific machine that you want to do that. But usually the schedule will coordinate. So if you need 8 of them, and you only have 10 servers, as you start doing your reboots, things will be getting rescheduled. So this guy goes down, his stuff gets moved to another guy that probably will go down eventually. So there's timeouts that we do so don't, flap services around too much.
Yeah, I mean that's abnormal shutdown, right? If I want to gracefully shut down a machine to upgrade, you need to, either you wait for the containers to come down gradually, right, from the machine, right, or reschedule it to the other one,
Yep.
shut down, right? Or you wait for a particular time, and then until then, you go to migrate, otherwise.
Yeah, you can say fleet, stop it on that machine.
Okay, so they do coordinate, like, the upgrade and the fleet.
Right, you'll see a lot of orchestration systems where you'll take down a few instances, move them, do your reboots, bring new services up, not necessarily move these, so then you kind of run at extra capacity, and then do these. So you can orchestrate that through the API calls, right? Fleet has an API, Docker has an API. A lot of these tools have APIs. Tools like Kubernetes actually have a reboot rollover mechanism built in for updating the individual container, but when you're rebooting the underlying host, the idea is that you've over-provisioned. And the way the reboots work in CoreOS, each machine by default will take a lock on etcd so they don't all reboot at the same time, right? So you can have a reboot policy of lock. So one will go to reboot, it locks the key, does this reboot, comes back up and unlocks the key. Put the TTL so we don't get stuck. And then you just roll out through your cluster.
I mean, all these things exist, or?
Yeah, that's here now. So yeah, there's a tool called Locksmith that's built into CoreOS. The whole updating system, we have a whole doc on it that shows you how we do updates and the different models for doing updates. Good question. You and me.
Yeah, so how do Fleet and Kubernetes work together? It seems like the Kubernetes also does Docker management, right?
But it has a lot more features. So Kubernetes will do things like integrate with CAdvisor. Kubernetes will do things like volume management between the hosts, permission schemes. It also has a service proxy. So if you have a container running here and you need to access it, so say you have 1 million servers, but the container is only running in one place. Kubernetes has built-in service discovery through a concept of call of a label. So when you launch a group of containers, you give them labels, and if you hit any other machine in the cluster, the Kubernetes proxy will send you to the right container without you knowing where it is. So it has a lot more features around a full-blown scheduler. Fleet's goal is for you to be able to easily deploy something like Kubernetes and manage more of the OS level. Yeah, some people have built full tools on top of Fleet where they do a little bit of smarts in their own, logic, and then when they made a decision, they tell Fleet what to do. So it's a very low-level primitive.
I see. So Fleet is at the higher level, at the host level, and then the Kubernetes actually does.
Yeah, Kubernetes is like
smart scheduler for
when you hear about Google's deployment methodology, That's Kubernetes. They always talk about a system called Borg. And Borg is basically this big system that understands all these things. And this is what Kubernetes is. It's the reincarnation of like Borg, done in a modern way, right? Borg is 10 years old. So a lot of the things that they wanted to do different, they're doing it now. Instead of a white paper, we're getting an open source project that people can use. You had a question?
Is CoreOS running in production anymore?
Yeah, to my surprise, I visit companies and I'm always like, wow, you're actually using etcd in production. So etcd isn't considered stable right now, even though people do it. The OS itself, we consider stable. So one good use case I've seen that fits the model perfectly are like gaming companies, right? You have these massively online games, and when two people want to play each other, usually you have to have a set of gaming servers. You gotta make sure no one's playing on them. But what they do is, two people want to play or group, they dynamically fire up a Docker container, use something like Fleet to say, hey, spin this container up, and then allocate that to that particular game. And when it's done being played, they destroy it. So, and they just run it all from memory. So they boot up the machines, they PXE boot them, no local install, and then just run an entire thing out of memory. Every machine has 256 gigs of RAM, everything is fast, and it just works perfectly for their use case. And those are some production applications. So we went stable about 3 months ago. So I would be surprised if it was a large install. So everyone is getting to the point now, they like the ideas, the products are getting solid, and other people are building other products on top. You got a question? Wait, I'll give you.
Yeah, so do you envision people coming off of something like Zookeeper to take advantage of etcd native?
Yeah, I've seen people make that decision, and it may not even have anything to do with which one is better or not, but Zookeeper was very painful to install, right? A lot of people ran into some roadblocks there. The algorithm that it uses is Paxos, and some people find it very confusing. RAP is much simpler to understand, so when people see how etcd works, and the way we made it easy to actually provision, a lot of people like the idea of etcd. It's just like a one binary you can put on a machine, and now you have this thing. No JVM, no other dependencies. The API is really, really simple. You can use curl to interact with the whole thing. So it's a very simple system that a lot of people like.
Is that in Golang?
Yes, all of our tools are.
Even etcd is?
etcd is everything. Every single tool we have is in Go, except for the kernel work that we have to do.
So you mentioned it gets dynamic IPs, right, from the same subnet.
Mm-hmm.
So how do I talk to another container?
Oh, let's show that really quick. I'm going to do this really quick. This will be the last thing I show. We got to wrap this up. So let's see what machines we have again. List machines. All right, so we're missing a machine, so let's start that guy back up. No, 0. We'll start it back up. It's going to come back and join that cluster. And what I'm going to do is I'm going to download 2 containers, just BusyBox so I can get a shell, and then we'll just use netcat to communicate. And we'll just see both machines, both containers that we spin up at that time, be able to talk to each other. So we'll do that really, really quick. But it just works like as you think it should, right? Since we're on the same overlay network, any IP that I receive from that bridge is guaranteed to be routed to any other machine in the cluster. So let's get this going. So we'll list machines, and we'll get on this first box. And then it just makes networking work the way you expect. No more magic, no more, if you're dealing with a cloud provider, you don't have to do any extra tricks because of the overlay. So we'll log into this machine first, and I actually have a little cheat sheet that I did, because I actually got this working before I left the office. So in one box, what we're going to do, we're going to make that guy the listener. So we're on this machine, and what I'm going to say here is, so even though I don't have BusyBox container on my machine, I'm going to have Docker pull it down. I'm going to get an interactive session. I'm going to run this bash command. Basically, I want to get the IP address of the container because I don't know what it is. And if that works, I want to start a netcat session, and I want to listen on port 80. So this is my container exposing the service. So we're going to pull down BusyBox from a repository. It'll take a few minutes. And let's see if the other machine is ready to go at this point. All right, so we're good to go there. What machine are we on now? 43? So we're on 43, so we'll go on 42 now. So we'll log into 42. So now we're on the 42 machine, and there's no containers running here. But we do have one running on this machine, right? So it's exposing port 80, and it's on this IP. So now if I want to hit that machine, and it works just the way you think it would work, right? I'm just going to download BusyBox container. and then we want to hit this IP address. So this is why etcd is very important, because when these services come up, they can publish their IP address in etcd, and another service can just pull it out. But in this case, we just got to do it manually. So here, we're going to say, download BusyBox, get a shell, and then use netcat to open a socket to port 80 on the other container. We'll let that install. And this is a big value add with the overlay network, because out of the box, you have to do a lot of extra work because of these dynamic IPs. So we're pulling this down. In a few seconds, we'll be ready. Wow, decent internet access. This is amazing. So I'm going to say hello here. And if I go to the other machine, we see hello on the screen. And then I can come back and say world. And then we have world here. So the overlay network allows us to basically have a truly distributed system where each container is a first-class citizen. And most people don't know how important that is until you try it without it. And then you have to do all this service discovery stuff. It's just a lot harder.
Yeah, I did that and it's a lot of pain. The problem I have is host names. Here you're not using host names, right? But there are many enterprise applications that don't give you IP address. They just say, announce their host names. But here, since Docker generates dynamic host names, there's no way, there's no resolver that sort of resolves that.
Yeah, so the key for most service discovery is you're going to get out of the host name business altogether, right? Because they're going to be almost opaque things. They don't mean anything, right? Because we're going to put the host name, right? You're going to put in DNS. Things are coming and going. You're going to have cache and validation problems. DNS is not going to scale at that level, right? Not for that. Maybe for your etcd clusters, you know what they are. But you're going to want to use IPs, right? Because you don't know where you are. Just because you have an IP that's not on the same network doesn't mean you can't route to it.
So that means we need to optimize, change our applications to support Docker.
Well, actually, applications don't need to do anything. It just needs to start up. That's the beautiful thing. So then, I know what IP you have, right? So you bind to port 5000. I know your IP. I'm free to take your IP address, put it in etcd for someone else to discover. You don't need to do anything, right? Like
How
all
do you
you
know
need
his
to
IP?
do, huh?
How do you know his IP?
I started you. You're the container, right?
Oh, okay.
I told you to run. I can say Docker. What IP does he have? And he doesn't need to know anything. Only contract you have is you provide service on the endpoint. So this is what Kubernetes does. It gives each app or a collection of containers a label. If I want to hit that container, I can look up a label and it will give me all the ports where they're binding. So it actually makes applications simpler. Don't do anything. Just log the standard out, bind to your port, do your work, and I will take care of orchestration for my schedule.
This is if I have control over the application that I'm trying to containerize. If I don't have control over the application that I'm trying to containerize, then I'm...
So what can an app actually do, right?
So,
an app can come up and do what?
Hadoop applications, for example.
Yeah, so what will it come up and do?
So you have a job tracker, you have a task tracker.
Mm-hmm.
And so the job tracker comes up and it says, hey, this is my host name, and it puts it in Zookeeper. And now the task tracker tries to resolve that host name. They won't...
All right, so you're talking about a system that assumes Zookeeper works a certain way, right? Zookeeper is doing, like, the Hadoop ecosystem is doing this for you, saying you're probably using Zookeeper, you're probably going to use host names, right? So it's putting you in a model that you can't do anything about, right? So in this world, we're talking about a very generic platform. Don't do that. Don't assume you know your host name. Like your app needs not to understand that stuff. It needs to the contract needs to be very simple. Bind to a port, receive traffic, and do work. If you do that, then I can schedule you. This is why most apps are hard to maintain. People that shell out to a command line utility, I change you from one OS to another, that command line utility is not at the same path, everything breaks. So to go to this model, we have to standardize. You can't do things that make your app less portable. So something like that, that's just tough to deal with, man.
Yeah.
But there's nothing stopping from getting the hosting. DHCP still works, remember, this is just a process. So we're getting DHCP, and if your DHCP is giving you a host name, sometimes what I do is I'll take my container ID and use that as my host name. But the problem is just host names are so slow to resolve, and they don't update fast enough. So I think there's better ways of doing that stuff.
Two questions. First one, more. Is there any way I can go through the steps you did and then get a feel of the whole thing?
Nope, I'm special. Sorry. Yeah. No, this is all really easy, right? If I didn't talk, it takes about 5 or 6 minutes. This exact thing that I did here, I usually write up all the steps that you can do almost on a copy and paste mode. So on our website, there are blog posts on how to set up just a basic cluster. And if you want to do something more complicated like I did in this thing, so this one will actually set up Kubernetes. A lot of people have questions about Kubernetes and a more powerful scheduler. If you go to this tutorial, once you have a CoreOS system up and running, this shows you all the commands, copy and paste style, that you need to do to launch everything else and do the exact same things that I've done here. I even have the cloud configs here that you can just copy and paste and do your thing. Yep. 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 And some people even have vagrant scripts, and you just do vagrant up and it spins up the whole cluster for you. So look on our website, there's a bunch of things that show you how to run one command and get it running in Amazon or your laptop. I have a lot of blog posts out there as well.
Can you increase the fonts a little bit about that, the address?
Oh, up here?
Yeah, the address, we can't see the address. How we gonna found it that,
Hold on. I got you covered.
Also, I can post that in the
Yeah.
meetup group comments.
Okay.
And send an email out to those who registered on SV Forum.
So that's the address. In my GitHub repository, I have lots of tools that show you how to leverage etcd, watch semantics, little utilities and guides on how to get started really quick, either single node or multi-node. And I try to give explanations of why I'm doing things a certain way. And on our website, we have lots of documentation.
Thanks a lot.
So you mentioned earlier that like this thing was like better for like 12-factor applications, basically stateful. Are you referring just to the Docker part, or like, I guess the question I'm getting at is, if I wanted to say deploy a database for my 12-factor applications, where would this go in? Would it be in Docker? Would it be in Kubernetes, or even external to this?
Yeah, so it will totally work. So the thing about the database part is data locality becomes a thing, right? So then you're gonna have to have special machines in the cluster. So you may have like 3 machines that are capable of running the database properly. Either they have a SAN attached storage, and then you may give them extra metadata, like this thing, database equals true, or SAN equals true. And then yeah, you could use Fleet to do that. You can say, you know what, Fleet, schedule this database, MySQL, and knowing that on the other side, it will always land on the machine that has the right data for you. You just gotta think a little bit more when you're doing something that isn't a stateless application, but it totally works.
So it's like basically specifying additional constraint that ties into it.
Exactly. Same thing with Kubernetes. Kubernetes can say, I need this volume. They're doing a lot of that stuff around metadata because databases get a lot more complicated because you can't just move those around. So you're going to use a lot more constraints. And I think a good recommendation is like partition those clusters off too. Like you're not going to be happy with your database server rebooting every time there's a new update. So you may turn updates off in that portion of the cluster and give it a specific metadata. Good question.
You use netcut to send hello world. Is there any kind of encapsulation or tunneling going on under the hood?
Yeah, so that's what Flannel's doing. Flannel's doing all the encapsulation for us. So when that comes out of the container, it's going to hit the Docker bridge. Docker doesn't know what to do with it. So if we do next-rn here, we'll see this route table here. And everything that's going to this 10 space, Flannel says that needs to come to me, right? Flannel will put a route on each host to say, anyone that wants to go to the subnet that I'm in control of, it needs to come through my interface. And then when Flannel gets the packet, it has that routing table in memory, and it says, oh, you want to go to this other container? Well, I know what that network is. It encapsulates another packet with the destination of the other host. The other host grabs it to the Flannel interface. It looks at it and says, oh, this is encapsulated. I'm going to break it open, and it sees that the next destination is a container.
Is it VXLAN?
Huh?
Is it VXLAN?
That's the next patch. So the first patch we have is UDP, much slower in user space. And what we have now is, so to our surprise, VXLAN support is in the kernel and actually has a simple API to use. So that's what we're going to do since we have a new enough kernel. So VXLAN and IPv6 support. So those two things will give us the right amount of security and performance that we need to make this a general solution.
So you're going to tunnel it even if the containers are on the same host?
You don't need to, right? Because when it hits it, you're like, oh, that's here, right? It's gonna find that itself. So nothing to encapsulate, just send it back.
So is there any protection mechanism at the OS level to avoid one container crash the pod system? So what happens if one app misbehaves? So that can crash the pod machine, right? So is there any protection at the OS to avoid?
So the container is really more of simple protection, like don't use too much memory.
Yeah.
Don't use too much CPU. You can't destroy the file system.
I mean, these are performance related stuff, but what happens if it goes some system code and that immediately crashes the pod machine?
So usually by default, Docker's going to remove the ability to call a lot of system calls by default.
Oh.
You have to do a lot of extra work to enable like a privilege mode, and you can specify an additional list of system calls you want. So what Docker does is try to make it easy out of the box by saying you can do very few system calls, and most apps don't need them. So that level of containment does provide prevention for accidents. Security-wise, the app has full access to the kernel. That is not as secure as a whole VM. Got to be very clear about that. But it does prevent mistakes like your app making a system call you don't want it to.
How do you set up a load balancer in front of a bunch of, let's say, running web servers in each container?
Oh man, there's so many ways. I'll show you a couple of ways, right? So early on, I wrote a tool called CompD, and a lot of people use it, to my surprise, to do exactly what you asked. I didn't intend to do that. I intended to be a temporary bridge between apps that can't talk to etcd to get their configuration. So what CompD does, it talks to etcd for you and resolves a Golang template with the values from etcd and restarts your app on your behalf. So this allows your app not to be rewritten. CompD does the work. And one of the docs that I have for this is like, how do you manage an Nginx config or HA proxy config, right? This is what you want. So what happens is, if you look here, here's an example. So I have all these template functions that allow you to do stuff, but don't worry about that right now. So here's an example of usage. You're setting these keys. Either you have what we call a sidekick process when you deploy an app. There's a little thing that runs on the side that's announcing the IP address of that app into etcd into a specific key space. So you can imagine entries that look like this. So this would be something that will be proxied in the future. The next thing we do is we have a Golang template, basically. And this is what CompD does. So basically, this little function here allows me to grab all of the things in that particular directory in etcd. I can take that and loop over that construct and start writing out my template file on the fly. And then down here, this is the rest of the Nginx template. So as those keys change, etcd will watch the key space, and every time it changes, I'll regenerate the config file. In the case of Nginx, I can just do a no-up or a config up, and then it will just reload its config, and in memory, you'll update your backends for your load balancer. And this is what the output ends up looking like, something like this. So if you have something like HA proxy or Nginx that's not aware of all these things, something like CompD helps. We even have, I think we even wrote a Lua module that runs in process with Nginx that talks to etcd directly. So when a request comes in, it goes out to etcd, gets the backends, and caches them for a period of time that's configurable. So we're starting to see more load balancers actually talk to things like etcd directly for this information.
So, assuming that I have a machine with 36 disks on it, and I want each container to use two disks, is there a way to not hardcode the disk that a container needs to use and randomly pick?
Once you get into that world, you just become less portable. So every special case that you add to the situation is less portable. You don't really want two disks. You want a certain amount of space and I/O performance. That's what you want.
But we are a file system company, so we want to write credits.
Yeah, no problem. So, no, ideally, you can actually expose, you still have access to all this stuff, right? So if you're running a container and you want to partition things up, so like Ceph running a container needs access to all that stuff. When you launch Ceph, you can just say, you know what, run in privilege mode. I want you to be able to read the entire system because you may need to be a privileged container. You know, if you're an admin, I know what I'm doing. I need this thing to be able to access all the file system stuff, all the device drivers for this. Allow the container to do that. No need to get complicated. Just do what you would normally do. So what do you do today? Do exactly the same thing and enable enough capabilities to do what you need to do. The whole point of this is to give apps the absolute necessary amount of capabilities to do their job versus downloading things and it's like, wow, why is this thing doing all of this? I didn't give it access to it. So by default, Docker pretty much turns everything off. You get upset because your app doesn't work anymore, and then you have to start adding capabilities back until it works. And now you have a better idea of what's happening. Cool, that was a lot of questions.
Regarding the fleet and Kubernetes, you mentioned about the difference between the role of fleet versus the role of Kubernetes. Is it very well understood? Is it that, you know, if I invest my time in fleet and Kubernetes, you know, with this assumption, will I ever get into an issue of the Kubernetes tech, like increase the role and vice versa?
So it's always a bootstrapping problem, right? So Fleet, we do not want to grow any more features. This is where we're happy with Fleet being done at what it does, and it should manage at the very low hardware level, OS level. And then some people, all they need is Fleet. They're using this as Fleet is all we need. We only have like 20 applications, 200 servers. We don't need any more things. Then they're finished, right? And then some people want Kubernetes, and we just want, how do you install Kubernetes? Well, on CoreOS, there's a package manager. So something like Fleet helps, right? If you want Fleet to manage the installation of Kubernetes, this is what we recommend. We've helped companies use Fleet to manage Mesos, right? These things need to get installed somehow. So Fleet is really nice to ensure that it stays installed and ensure that it stays running. Once it's up and running, you talk to that directly.
But Fleet requires you to use CoreOS?
Nope, Fleet's ready to go, you can put it on another system.
So can you compare CoreOS with GearD from Red Hat?
So GearD, so they have their platform OpenShift, and there's more of a PaaS platform, right? More of a Heroku type thing. And they had all these components. Like, I can imagine their product team being like, oh my God, now we have to change everything. Not because it wasn't working, it's because people agreed on a new standard. So OpenShift was really innovative. It came out with a nice PaaS type system that gave you these cartridges, containers, and you had this ability to package things up. And if you did that, then GearD can move them around and schedule them. And it would do things like Kubernetes and update key store and hide all your metadata. And everyone looked at that and said, wow, we don't do that. It's not standard. People felt it wasn't standard. So when Docker came along, Docker wasn't tied to one system. Right? Docker said, we don't care who uses it as their underlying packaging format. So when people jumped on that, if you look at the new version of OpenShift, it has Docker, has OpenShift, it has Docker, has etcd, and has Kubernetes, right? Because those are the components people want to see, right? So the overlap is people agree that the model of pushing containers around and using schedulers is where we want to be. There's a lot more work to do, and you're starting to see a lot of projects converge on the same ideas. And then we'll get back into a commodity market, and we plan on just being the leaders in that space. That's just where it's going for us. Cool. I have a couple of t-shirts and stickers to give out. We're very close to 9 o'clock, so I think we should stop it there. Hopefully this is useful for you. I don't have a lot of t-shirts, so if you want one, you have to, you can tweet about this meetup, and we'll try to get you one mailed out to you, but I do have a few. I do have plenty of stickers, so if you want them, please come up and get them.